So I had a request to just clarify on the activity that you have on fluid dynamics, and then also just to maybe expand on some of the math relationships that you don't have to do calculations for, but just to understand the concepts. So first of all, the activity is the two-paper one at the towards the bottom of the page in the text, and it has two different steps. The first step involves only just one slip of paper, and you can see my amazing artwork here. Basically, you just hold the little strip of paper between your thumb and forefingers and let it drape over the front of your hand as you hold it up near your lips, and then blow straight over the top of your hand. And kind of spoiler alert, I've shown you what will probably happen on that one. So that's step one. And then the second one says, hey, take both strips of paper, hold them side by side up next to your mouth, and hold your fingers out so that there's space between them, and then you're going to blow between the two strips of hanging paper. And of course, the size of the paper isn't that important to be able to do this, but just do that quick demonstration. And then in terms of the math relationships that I'm going to expect you to understand in terms of concepts, there's two big ones that we're highlighting. One's called the equation of continuity, which says that the cross-sectional area times this fluid speed stays constant, basically. So since the fluid can't disappear, then if you have, in this picture, you have all this fluid moving from left to right, the fluid can't disappear. And so if the fluid is going to have to squeeze through a smaller space in order for the same amount of fluid to go through in any given time, it's going to have to speed up. And I always liken this to, getting out of chapel, right? If the opening getting out of chapel is really, really small, then the speed that people can go up the steps as they leave chapel is much faster than the speed that we back in line, waiting to get through the door can go. And so anytime the cross-sectional area decreases, the speed increases, and vice versa. If the area goes up, then the speed goes down. If the area goes down, the speed can go up. There's lots and lots of applications of this. I mentioned rapids and hinted, hey, what's going to happen to the river? It's going to change area somehow. There's two options that its area can change. Squirt guns work this way, right? Spray bottles, the tube is fairly large, and then it's going to go through a very tiny hole. And when you change from the wide tube to the little tiny hole in the nozzle or the spout of the gun, then the area gets really, really small, the speed gets really, really big, and that's what causes the squirt gun to shoot out at a fast rate and goes far. By the way, we call this bottlenecking, right? You see it in traffic as well. As fast as people can go when the construction narrows it down to just one lane, everybody backed up in traffic in 3 and 4 lanes is having to go much slower than how fast you'll eventually get to go when it gets down to just one lane. Bottlenecking, we see it in rapids, we see it in the other example I mentioned in the assignment of putting your thumb over the hose, squirt bottles, guns, water guns, things like that. And then the other one is the relationship between the fluid speed and the pressure. This is known as Bernoulli's principle. It gives us Bernoulli's equation. But again, you don't have to do any math, but I do want you to think about the concepts. And the concepts have to do with if the fluid is moving faster, then the pressure is lower. And I give you an example there at the end of the device that uses the difference in the speeds to measure, or the difference in the pressure to measure the speed that wind's flying. The other example you'll see is if you're driving down the highway and you crack your window, then the fast-moving fluid on the outside of your car creates an area of low pressure, and if you have like a receipt, it might get sucked out the window, something like that, because the fluid moving on the outside of your car is moving faster, and therefore the pressure is smaller. They also have other, if you read the figure and the descriptions of the figure, there's other examples that I normally do in class. What's called an atomizer, like an old-fashioned perfume bottle. If you squeeze the bulb of an old-fashioned perfume bottle, it makes the fluid go really fast over the top of a little tiny tube, and that will make low pressure draw the perfume up into the stream of air, and that's how you spray perfume all over yourself. On a windy day, go into your bathroom and look at the water in the toilet. If it's really windy outside, the water in your toilet will kind of be rocking back and forth. The fluid level will be rising and falling. And the reason is the vents on the top of your house are like little straws. And when the air moves really fast over the top of those little tubes, it creates an area of low pressure, and it sucks water up into that vent tube from your toilet. But then the weight's too big, so it falls back down, and that's what causes the water to rock back and forth in your toilet if it's really windy outside. So when it's really windy recently, or sometime soon, go in your toilet and stare at your toilet water. Anyways, hopefully this helps put some clarification to some of these important concepts.